I think it's important to prepare ahead. So this talk is going to be about geologic decision support models that can be used for mining, groundwater, and mineral exploration applications. The outline for my talk: first, we're going to give a brief introduction and personal background, followed by a work story, which for me will involve field investigations and developing geologic models, some key skills for this career, and some recommendations. So my career path, I got a Bachelor of Science in Geosciences here at the U of A in 2010. Places I worked as a research assistant in the isotope ratio mass spectrometry laboratory here at the U of A, the tree ring lab. I actually found out about that position in the CES club. The professor came and advertised, I need lab assistants to anyone, and so I went running over. And then I submitted my resume to Ann Chase and got another position as a research assistant at the Arizona Radiogenic Helium Dating Laboratory with Pete Reiners, and did that for the last 2 years of U of A. From there, I became a hydrogeologist at Montgomery Associates, based here in Tucson, and I'm still working there. I got a PG, professional geologist license in Arizona in 2014, and then in Texas by reciprocity in 2017. So I'm just interested, show of hands, who here works at a research facility at the U of A or has worked? It's a great opportunity here at the U of A to network, get work experience, and a little paycheck. So I highly recommend it if you haven't already. Looking into any opportunity you can go volunteer here. These bullet points were bullet points I used on my resume that I submitted after college. And it seems like really simple tasks, but it really just shows that you do what you're asked, you're good at working with others, working independently, taking responsibility. So, sometimes analyzing prepared results in Excel seems pretty simple, but, doing it and getting a little paycheck showing that you're doing it attentively really is a great opportunity here at the U of A. And chronologically recorded detailed procedures in a logbook, perform maintenance, calibration, troubleshooting. And one other, for those who are working at lab, there's so many opportunities here at the U of A. Another undergrad and I ended up doing a joint project with the Honors College. You can submit for applications to get little grants, and then you present at an undergrad poster symposium. They publish your results. It's just and I put the award it was, so you can look it up, or I'm sure there's other opportunities. Just another opportunity for those who are already working in the lab. And here are some of the bullet points from the Arizona Radiogenic Helium Dating Laboratory that I used on my resume. Again, just another example of attention to detail, working with others, and working independently. So leading preparation of samples for analysis using microscopy techniques, recording data accurately with appropriate details, and safely labeling and organizing samples, entrusted with samples, training visitors. And I kind of laughed when the resume people said, put this one, maintain cleanliness and integrity of the lab. And I thought, that's just part of the job. But that's important. It's part of the job. You did what you were asked to do. You can't be stressed enough to really learn how to sell yourself. So after graduating, I became a hydrogeologist at Montgomery Associates. Montgomery Associates provides water resources, consulting for mining, municipal, industrial, tribal, governmental, and other clients since 1984. Some of their services are water supply and recharge, mining hydrology, environmental hydrogeology, hydrologic modeling, water resource planning, water rights and impacts, and data management services. Just giving a background of, we do a lot of stuff, all water related, but a little bit more. Our corporate office is in Tucson and branch offices in Phoenix, California, Colorado, Nevada, Utah, Argentina, Chile, and Peru. So just some background of the company they work for. What I do at Montgomery Associates, I've had kind of two roles. First, starting off, I did lithologic characterization of basin fill and hard rock environments. Pretty fancy words to say. I was the boots on the ground doing drill cuttings, logging them. And then I did field support, which involved well construction and development oversight, conducting pump tests, sampling, and monitoring rounds. 2 years of that, and slowly transitioned after taking on that responsibility, spending your time in the entry-level position, proving yourself, and then slowly transitioned to developing 3D geologic models, incorporating borehole data, geologic report sections, and surficial geologic maps to support mining pre-feasibility studies and groundwater flow models. These can lead into resource estimation, and I also spent some time doing water resource decision support models, quantifying uncertainty, and simulating outcomes. I make it sound like it was 2 years there and then all of a sudden hard shift over, but it was a slow, probably 2 to 3 years of transitioning, spending some weeks in the field, some weeks modeling. So it's always we start off at the entry level and it takes time to grow into the next position. And I would say most employers are cognizant of that it's hard to move from one position to the next. So just know that it's okay to take time to transition. So for my story, moving on to the work story, I think especially for geologic modeling, and one thing I can't stress enough is that I think it's really important to spend some time boots on the ground. You really get to know the job from the ground up. And so entry-level experience builds a strong foundation to confidently make decisions and understand data collection processes. And I think it's critical to understand how the data is collected, interpretations from the log, or inherent assumptions. It really helps to build your model when you understand the whole process of the data collection. And the best way to understand it is if you spent some time doing it and know some of the logistics behind it. So rather than spend all the time talking about the nitty-gritty of modeling at the very end, I think it's important to go over some of those field investigations that are so critical to the model and really hone in your geologic skills. And that's why you can see just from this list, it's really geologic based. I kind of laugh a little bit when sometimes someone says maybe a non-geologist should do the geologic model. Well, it takes a lot of geology to really take ownership of it. So some of the field investigations, you guys do a lot of this already when you're doing your field visits, but reviewing the geologic reports, just getting background information on the regional setting, and doing some site-specific background. Understanding the stratigraphy of the site, knowing what units are there, the formation names, geologic unit key characteristics and markers, which beds have faults, which beds have a marker shale, which beds have some fossils, what faults might be around if you expect to encounter a fault when you're drilling, interpreting the geologic map surrounding a drill site, and lithologic characterization and field logging techniques, geophysical log interpretation, and importantly, documenting your interpretations and field activities. Can't stress enough taking notes. So I'm going to go into depth a little bit about some of these key aspects of field investigations, especially those that are important for geologic models. Interpreting geologic maps. I know you guys are all really savvy on this still, because you're still doing it a lot. But this is just a map of the southern end of the Tucson Mountains, and just taking the time to look and see if I was going to drill a well here, what units you would expect to encounter. If you expect to find a tuff, you would probably guess that it's this tuff, the KCW versus the TKB tuff. I think it's important when you go to a drill site, just always having a map with you and knowing what to expect. Don't know how many times I've received a log from a geologist, and they say, we first encountered the limestone, but the drill hole started off next to basalt. How is that possible? Or, you started off in alluvium, You didn't log any alluvium. So just taking a moment to look at the geologic map, make sure it makes sense while you're looking at the drill cuttings. So lithologic characterization. Has anyone here looked at any core, any rotary chips? Always, or do you guys always see them in hand sample? That was probably one of the most shocking into the workforce experiences I had, was trying to look at rotary chips and trying to think, what rock is that? And just thinking, gosh, I actually went back to the U of A to, I forget which room it is, but the first introductory class, and looked at all the hand samples, just thinking, okay, if this was kitty litter, which rock would this be? Just trying to, anyway, so just knowing that there's different types of drilling methods, and knowing your data inputs to your model. Do you have highly detailed core where you know there's very little mixing, you can see the contacts literally right there? Or sonic core, which is pretty intact, but still a little mixed, or do you have rotary chips where you do have some mixing and the contact isn't quite clear, but you have other techniques to hone in on contact? You might ask why we don't just always do core. It's very expensive, and it depends on what you're trying to do in the long run. If you're trying to install wells, you need to do rotary, so that way you can have enough diameter to install well casing or production casing. Sonic core is a little smaller. Sometimes we do piezometers with those, and core just quite small and slow going drilling and expensive. That'd be interesting to look at the rotary chips a little bit and just think what type of rock. I thought about asking you guys what type of rock you thought it is, but it's really hard with just an image. You really have to spend time logging, looking at every little rock chip, trying to understand which rock. And so when we're doing rotary chips, a lot of times, it's drilling down and we log a 10-foot interval. Yes?
What's the scale of that picture?
Each box is 10 feet of drilling. So that's 400 feet. The outcrops, here we have a tuff, and so over here, it's a tuff. And you can see it starts to change into this lighter unit, and then into a black unit, which is this vitrophyre. So it's a tuff, a basal tuff, and into a vitrophyre. The next thing you might ask is, where are the contacts? From the tuff to the basal tuff, you could say, maybe it's there where you see the color change, but it's kind of a gradational contact, so it's really hard to pick it out. Versus the vitrophyre to the basal tuff, it's pretty clear. You get the basal, it's somewhere in this 10-foot interval it happened. But it's interesting you see that there's still some basal tuff in this sample. And so it's just that interpretation. On paper, someone logs it and you see there's 10% basal tuff all through there. But just putting on your digging hat and realizing that can be contamination from above, just knowing the drilling method, that when you're drilling down and you're drilling down further, that some contamination can happen. And so even though part of the record has some basal tuff, that it's actually all in vitrophyre. Some of these things, just taking time, doing some of the logging, you tend to learn over time. Some other field logging techniques that we do, up here we have a very detailed description of one 10-foot interval, a lot of time spent on one interval just trying to better understand it. We go through the color with the Munsell color chart, going over how well lithified it is, doing the composition of the fine sands and gravels, what type of units those clasts were in the conglomerate, and the reaction to acid. Going over how angular the unit is, sometimes using the Unified Soil Classification System. So a lot of times spending just documenting each little interval to better understand any chance we can of knowing where there might be fractures for the secondary features, noting when we see iron oxide, calcite. and just documenting everything you can while we're in the field. So with the rotary chips, you can see that the contacts sometimes aren't quite clear. A lot of times we use geophysics to refine those contacts. And they show the variability of the units a little more unmixed. These logs show SP on the left. These are two different logs. They show SP on the left, spontaneous potential, and resistivity on the right. These are just 100 feet depths. And the unit it's showing in yellow is a sand for both of them. And you can just see that if you took a 10-foot sample when you're drilling rotary, you have 10 feet of mixing through here, you really wouldn't see that maybe the contact was about there, because you would have some mixing through here. And it wouldn't be until maybe down here when you realize that you were out of the sand and the shale. So when you're trying to screen your well, this really helps you know we need to screen our well up here in the sand and try to avoid the shale down there. It's interesting to know that this is the same formation and that the characteristic can change quite a bit across sites. Just thought it'd be interesting to go over some other things you can learn from geophysical logs. They really help us target fractures. This is a acoustic borehole image, and you can see it takes an image of the borehole and then splits it open. So you can see some of the fractures. And some of the wells we've done, we try to target vibrating wire piezometers, that way we can measure any pressure differences in these fractures, so we can measure head. And so this could be a fracture that we would target based on the image. For geologic modeling, this can help quantify RQD if someone's modeling RQD data. So for modeling, really just knowing your data inputs and the confidence of the data. You can see this example, this is one well, just how much information we have about this one well. We have the lithology, the percent fine sand, well, this is actually just the time it took to drill, and all these geophysical logs. We had acoustic borehole viewers all throughout, sonic log, resistivity, caliper, gamma. We even took time to review that acoustic borehole image to see where we thought there was lots of fracturing, which is the dark blue, light blue. So you can see we saw lots of fracturing down here. We encountered water here, so we screened the well there. So lots of information, lots of confidence in this well. Versus, sometimes you might have a well information where you don't know a lot. Down here are two logs that were sourced from the Arizona Department of Water Resources image well records. And you can see it's just it's just drilling records that the drillers have to provide some geology for the wells they drill. Sometimes you'll get lucky when you look on the record and you can see this person obviously knew the geology. They put alluvium, canal schist, granite mounted porphyry. This log on the right, you have topsoil, sandy loam, clay and conglomerate, broken conglomerate. Still informative, but you're still basing your interpretation on their interpretations. So just knowing the level of detail going into the model, what the data inputs are, were assumptions made before you even got the data, or was your organization part of those interpretations? I've seen some funny drill logs after looking at them. Sometimes you laugh and you see a driller say red rock, brown rock. But sometimes if you look at it, that green rock, there's only one green rock out there. So it actually is a cool diamond in the rough when you find that. But sometimes they're not very useful. Sometimes they're very descriptive. They're colors of browns. So again, I think spending some time in the field, which is also an easy transition into almost anything else, taking that responsibility is a good start. But moving on to developing a geologic model, I went over just kind of what I see as the general process. First, starting with the meeting to determine the project goals and requirements, evaluating and preparing data inputs, importing data into the geologic modeling software, spatially analyzing geologic or hydrostratigraphic data, and developing a geologic or hydrostratigraphic model. And then depending on the purpose of why you're doing this model, you might stop here if you're just trying to visualize the model, or you might use it to evaluate to the numerical model grid for a groundwater model, or develop a resource estimate for a particular analyte of interest. So moving into, deciding the purpose of the model, meeting the model, what's the purpose? I listed some purposes that I've been a part of. It's just improving the big picture, understanding the site, and visualize what data you have. It's really cool to take all these paper copies and put them in 3D, and just some things come to life and you understand the site a lot more. We've done it to support mining feasibility studies and supporting groundwater models, bringing it all together so that way they have an easy data input for their groundwater model. And can lead into mineral resource estimation. And importantly, sometimes, depending if you're still out there drilling, it can be a tool to predict and determine the next best drill site. A meeting to determine the model goals. I can't stress this enough. It seems pretty straightforward, but I don't know how many times, sometimes someone says just run with it, go with it, but really just slow down and take a moment. In anything that you do in life, when you're starting a new project, take a moment and think it through. Think about what level of complexity is needed. Do you really need to model every unit you see on that geologic map, or can we simplify? Simplify where you can. I just put this because I deal with it a lot. What coordinate system are the data inputs in now? What coordinate system should the model be in? Sometimes just formatting the data and getting it all on the same level playing field takes some time. But it's important to make sure everyone's on the same page and everyone wants to use the same coordinate system so that way there's not any issues down the road. What are the units of interest? Is it geologic or hydrologic? So with geologic, you guys all know that's anytime you have different lithologies, different formations, but sometimes with hydrologic models, we group a lot of geologic units together just because they act similar hydrologically. Extent of the model domain and the resolution. We do cells that are a mile or 500 feet. It really depends on what the purpose of the model to answer these questions. What limitations and assumptions are acceptable? So I've been a part of some models where they really just want the best idea possible. So that's in using the data inputs and geologic interpretation to make sure it makes geologic sense. And I've been a part of other models where the client said, look, I just want the data, try to limit any interpretations as much as possible. So just knowing what the client wants and timeline. Make sure it's achievable, what you're trying to do in the timeline provided, and knowing that there's a timeline. Some geologic modeling software, and this isn't all of them, and they're not in any particular order, but some geologic modeling software out there is MineSite 3D, Leapfrog Geo, Vulcan, Voxler, Petrel, Surpac. Just curious, have any of you guys heard of any of these? Used any in the lab? Yes?
Did you have any experience with any of those before getting in the industry?
I did not. Learned on the job, got training. But I know that a few of these do have opportunities to get academic licenses. So I can't really speak completely, but maybe just see if there's any opportunity. And I think that's one great thing about the U of A is just reaching out to someone and saying, hey, I'd like to try a software, and just seeing if you can. Because a lot of these are very expensive and you won't be able to do it when you're out of academia easily. They have sometimes good price tags on them. So then evaluating, and that was part of the decision is what geologic modeling software you're going to use. We use a lot of the same one, but it's just important to know if your client wants something in a certain model to software to use that. Then on to evaluating and preparing data inputs.
Can
Yes.
I ask, so while you were here, what programs did you have experience in?
Not enough. I wish I had more. Not, I wish I had spent more time in GIS. I think that's something I've heard across the field in my levels. People always wish they had more time in GIS. I think it's something I use every day now. But other than that, I didn't use a lot of software. I did probably, but I can't think of it immediately. But just taking the time to really get to know Excel, get to know Access, a lot of that I did after leaving the U of A when I realized what I wanted to do. And so I fine-tuned it and spent extra time kind of fine-tuning my skills in personal development outside the office to try to succeed. But it's hard when you're not sure where you're headed or how you're going to use the tool, it's hard to prepare. So I think at this point, just putting your fingertips in every little thing you can for it while you can here. Until you know, but Excel and Access I think are definitely good things to know pretty well.
And so we do have a programming requirement for all three of our subplan areas. And so some of those examples are Python, and we do have a MATLAB class now.
Okay.
And then there's a C++ through electrical computer engineering, and then of course GIS, several different GIS options. Out of those, are there any particular ones? I know you said GIS. Are there any others you would highly recommend that the students get experience with before they?
Definitely GIS and Python are the first two that come to mind, just knowing what folks use at my office a lot.
Mm-hmm.
I know the curriculum's changed since I came. I think one of the options, maybe you guys took the easy option, I can't remember what the options were, but I took Java. And yeah, I think the MATLAB is another one. It's definitely, out of the options, those three would definitely get, if I could come back for a class, I would come back for any of those. So that's great that good to know that that's part of the curriculum now. A little more fine-tuned. So evaluating and preparing data inputs, again, the well coordinates, going out with the GPS, getting a well survey. You think all wells aren't drilled plumb. Sometimes they go off at an angle, sometimes on purpose, sometimes they just do a little bit. Just that's the nature of drilling. Just knowing when you say your contact is 30 feet, or I said 3,000 feet below ground, but your borehole went off at a 2-degree angle, it's at a different depth than if it was straight plumb. You can see in this model, we just made the assumption that they're all plumb. Didn't want to spend a lot of time on that, but when you're doing mineral resource estimation, that's critical to know your DDH hole, your diamond drill hole went off at a 45-degree angle, your resource is over there at 3,000 feet, not right here at 3,000 feet. And then taking your lift log and deciding on the model units. So for this lift log, you could see, we got rid of all the lift about it, but you can see we had a geophysical log, and from this we made a few units, 1, 2, 3, 4, 5. And just simplifying it before it even goes to the model. So all we have to model is this contact, this, and this. Really simplifies the process and make sure everyone's on the same page before it even goes into the model. Down here is a screenshot from one of the geologic modeling softwares. You can see the colors are the black dots, and just the site has a lot of data. You can see, even with all that data, if we just started off with sand, gravel, it would be a nightmare. So simplifying it before it even goes in really makes the picture stand out. You can just immediately see, this, sorry, I made all the colors similar, but you can just see that they're dipping down this way, the beds. That's maybe another point. You guys deal with this still all the time, but knowing that geologic unit colors are important. So they all look the same, but as you know, color in geology is important. And then in the GIS, it's very important. I can't imagine being able to do geologic models without learning a little bit of GIS, just so you can prepare your own data sets. So outcrop polylines. Here, this is in East Texas. And describing the outcrop polylines. Often those are already digitized by government agencies, so you don't need to go to a paper map and draw it in yourself. A lot of the time this is already available. And it's not as simple as just grabbing their data and running with it. At least in the software I use, you have to use one line where it's touching, if you're gonna model one unit, for instance, this unit, this orange unit, you would want to model it as it was deposited, so only where that unit touched an older unit. So you have to kind of take some time to analyze the data, prepare it, and get it into the software. And then structural features. You know, you have all these faults, just knowing that there's an abatement, an arch here, another uplift zone. What of these structural features do you want to bring in? You can't model every single fault. That's too much computational time. So do you simplify and draw one fault through here and say does that fit the purpose of the model? Is that okay? And in this model we did that. And these little faults were inconsequential, so we ignored them. But just taking the time to grab this GIS data, work with it spatially, and get it ready for the model. Stereo nets. How many people think you would use a stereo net after school? At least one of you. Yeah, so if you have it available, or even just any map, strikes and dips really help to influence the model. How's the bed dipping? Especially in this area, we had no drill holes. How are we supposed to know? Well, luckily the AZGS already did all the work and we brought it in. And especially in areas, maybe like over here, where we had no structural data, but the unit showed up again. How do I decide? I need to add one interpretive strike and dip to have it help, keeping it separate so I know where it was actual data and where it's me adding interpretations. But how do I know how to set it? Well, there are all these in a stereo net, and I know in this region they're always plotting over here, so I know it's best to use that kind of strike and dip. And then bedding and fault orientation. Sometimes when you have a fault, there's a fault orientation nearby, but just outlining the fault in GIS and preparing it and making the decision beforehand, especially with a lot of models I work with, it's a hot topic. Is the fault dipping this way or that way? Are we going to treat it like a steep angle fault, or is it going to be shallow? Just knowing the regional geology and having some justification if you have no information about that fault, and just saying, I made the assumption it's a high angle normal fault, 45 degrees, based on the regional geology, just being able to document why you did what you did is at least something, rather than just, I have no idea, just did it. So just taking the time when you're evaluating and preparing the data to think about how to do it, why you're doing it. There's other areas where we have no drill hole data, but a lot of government agencies have spent time in the field. And they have cross sections. We can bring in those cross sections into the model, and sometimes I've brought them in and just added a couple contact points and said, this model is based on drill hole data where we have it and published sections where we don't. So just another utilizing published geologic sections where you can. I skipped over importing data because that is an important step, so I left it there, but it's not really much of a step to talk about because we've been doing it as we've been evaluating. Spatially analyzing the data, doing exploratory data analysis, EDA, just taking time to see how all these pieces come together and interact, getting time to know your data. Did the different data sources agree? Do you have a drill hole that was, that geologist put that limestone there, but it's in basalt. The outcrop is basalt. Making sure they all agree before you're spending time using the data. Are there data gaps? And any assumptions that need to be made immediately, such as that fault and what angle it's going at. Moving on to developing the geologic or hydrostratigraphic model. So this is a screenshot setting up the model and unit relationship. This is the screenshot of one of the softwares where it shows the little package where you make the geologic model. So you set up the boundary. In this case, this was our model boundary. You decide your fault system. So if you you cut up this big volume with different faults, you set that up, which lithologies you are going to be able to select, and then a surface chronology. And I think this is one of the times where it's not just button clicking. This is where a geologist has time to shine. So this is setting up your stratigraphy, you have different surfaces, a deposit, an intrusion, this is an erosion surface for this one, and then setting up the relationships where you have unit 2 always touches unit 3, unit 1 always touches unit 2. This stock touches multiple units, so that's why, and it came in later after all these were deposited. And then you have this quaternary alluvium that came in and eroded, and it touches multiple units. It's not always straightforward. Sometimes you have to switch things up a little bit, but just going over the unit relationships. And when you build a surface, it's building a volume on one side and another. So that's where even though the stock does touch other ones, you put multiple. So that's just one example of one software, how to set up the stratigraphy. And then eventually it makes some volumes. And that's very simplified, there's more to it, but it's a start. So after you go through all those surfaces, you have, in this case, in East Texas, we had these units. So we had volumes for each of these. And after you have at least a couple of volumes put together, it's great to just spend some time interrogating the model. Look at it in plan view. Does it match the outcrop map that you expected? Rotate it around, slice the model, view sections, evaluate it to the published sections, back evaluate it, make sure it's what you expected, and just look at one unit at a time. Make sure that that one sedimentary unit doesn't have one huge bulge in it. Just spending time with your model. And just thought it'd be good to go over, again, just documenting your data sources, your methods. Where did you have data? Where was it from? When did you make an assumption or interpretation? And that, I guess that goes in and ensure your assumptions are clear. And make decisions. I think some of the best modelers are people who make a decision, say, I did it because of this. I'm willing to change it, but this is why I did it. But don't, sitting there and hemming and hawing over something doesn't help us stay on the timeline. And have justification, whether it be data-driven or geologic expertise. I don't think I have seen to date one model that has been built completely on data with no geologic interpretation added. It's just the software doesn't do it all on its own. And sometimes you stop there because you just want to visualize the data, but some of the other purposes of the model is evaluating it to an numeric model grid or a resource estimation. This shows a section of our geologic model and the numeric model grid, which they discretized cells heavily over here where they were of interest, and then they made the cell blocks larger. So you can see, just knowing that the modeler wanted his cells to be like this dictated how fine of a resolution model we had to do. So we had to make sure that where he needed detail, we were really on point. But over here, where he didn't need detail, we didn't spend a lot of time. Just made sure it matched and made geologic sense and left it at that. And sometimes, this is just one example where numeric modeler can add other attributes. Mineral resource estimation. Is there any geostatistics at the U of A now? Any of you interested in mineral resource estimation? So there's a couple softwares that do it. LeapFrog-Edge, SGEMS, ISATIS, R. GIS has a geostatistical analyst package. I haven't done too many of these. I'm not a geostatistics expert, but one thing after we've done is, after having all the volumes, is where do we have this analyte of interest, where does it exist within that volume? In this example, we have lots of samples. You can set up your variogram to see where you have data continuity. So rather than just letting some contouring go crazy and say, you have blue here, keep connecting all the blues, we're trying to look for where we have continuity. So statistically, our contours make sense, and where we have the most correlation in one direction, the major axis. And so as we go further away from a sample, it starts to correlate less and less and less until it reaches a certain point where we say, don't correlate that sample anymore, that there's no more influence. And so, in the minor axis, here you can see until we reach that point at a smaller distance. We didn't want to correlate that sample further that way. And then the z-axis, there's some correlation to z too. So we used this to do some contouring of the analyte of interest in that same software package. And we're able, in this case, it's one method to come up with a mineral resource estimation.
But it can be used for lithium, which is a mineral that's being looked at a lot now for all the battery technology, right? So this has become a tool that we've used in-house.
This is a common tool. We use it for a couple of projects. A lot of people think of mineral resource estimation for copper, for gold, but yeah, we've been using it for lithium brine resources. Which is a little easier because when you hit the brine, you're not gonna, when you're in a vein of gold, you can hit or miss, that there's less continuity, so it's sometimes a little easier. I guess that's one thing I should add here, in the Z, when you have some distance from here, that means it's not showing Z. But for diamonds, the nugget's pretty high. You don't know, when you put your hand in, you're gonna get a diamond. You put your hand almost in the same spot, you're not gonna get a diamond again. In lithium, the nugget's pretty small, where you grab a sample from 300 feet, you have lithium, you're gonna do it again, you're probably gonna have lithium at least in the same time. Over time, it goes down though. So key skills for this career, and again, I'm a good example of, I didn't leave the U of A saying this is what I'm gonna do. I have everything I need to do this. But this is what I would say is a strong foundation to start in that path, is a strong foundation in geology core courses, the fundamentals. They said I came back and looked at rocks, structure, stratigraphy, regional geology, just knowing the big picture. I put Excel, Axis, GIS, and don't need to, but geologic modeling program, just if you can, it would give you one leg up to see if there's an academic license. Some field experience. For my resume, before I even left here, I put the hours of field. I looked at all the days I spent at the U of A in field camp, all the regional geology field courses, and I worked 670 hours field experience in undergrad courses. So just maybe even calculate how much field experience you are trying to do if you're trying to get a field job. Shows how much time you spent out there. Documentation and communication, troubleshooting skills, making decisions, and if you want to do mineral resource estimation, geostatistics. Recommendations I have, again, ensure you have a strong geology core foundation. I say synergize capstone courses, but ensure there's some variation. In my experience, I really thought when I was leaving the U of A, I was really into geochronology. I really wanted to go to Antarctica and do those ice cores. It was my cup of tea, but it wasn't. I was really glad that even though I took that one capstone was what I wanted to do, that I took some other ones, and those were the ones that ended up leading me to kind of learn actually my passion. Once I got to do some time in the workforce and understood a little more what I liked. Talk to people who already work in the field you were interested in. And also talk to those who are in other related fields, but not necessarily fine-tuned in that geochronology, but move on to other ones to keep a wide horizon, because you never know where you might end up. Make connections at the U of A, professors and students, and keep them. I wish I kept a few more connections at the U of A. But it's easier to keep connections than make new ones. Seek opportunities to work part-time in a research facility. There's good opportunities here at the Geosciences department. There's the rock room. Even just submitting your resume to Ann Chase, there's other opportunities with the hydrology department, the tree ring research lab. There's other guys around here. And if you're working in a lab, seek a research award opportunity at the U of A. In my case, I didn't come up with anything groundbreaking. I just talked to my professor and he's like, oh yeah, I have this side project I've been wanting to do. Oh great, that works out. So you don't necessarily have to come up and invent a new wheel to do that. Can't recommend enough, before graduating, go to the resume center. at the student union to learn how to really sell yourself. You saw from my examples, my lab positions, I always thought they were just part-time work, but it really helped me learn how to sell those qualities. Good exposure to software available at the U of A. You don't necessarily have, well, I guess you guys do have to take a class, but even if you don't have to take a class in R or GIS or MATLAB, just take a little time and learn the software a little bit, get your feet a little wet, even if you don't end up taking that one class. Be involved with organizations. Networking is important. Internships are a foot in the door. My position started off as an internship, and I think it's a really good way for you to get to know a company, for a company to get to know you, and they're a good way to get your foot in the door and some experience underfoot. So I know it's a little scary when you leave the U of A. You want to get that job that you're going to do, and you know you're going to be doing it for a long time, but they're a great opportunity not to be overlooked. They do lead to jobs too. Look for opportunities to distribute your resume. I don't know how many of you have started looking just at what jobs might be out there, but it never hurts to just contact a company and just say, hey, can I send you my resume if anything comes up? Just mentioning that you can look for opportunities. Pursue your geologist in training and professional geologist designation sooner than later. It gets harder with time. With the GIT, you have to take a test that really stresses your academic smarts. So the longer you wait after college, the harder it gets, especially with kids. Get comfy with life, it gets harder. So definitely do those sooner than later, and don't be afraid to step out of your comfort zone. I took that from your talk a little bit, but you just never know where you're going to end up, and don't be afraid to try something different. I certainly didn't think I'd be up here talking to you all and doing what I do 10 years ago, but still stepped out of the comfort zone and tried something different.
Well,
Any questions?
So how did you find out about the internship that you got that eventually led to you getting a full-time position?
Networking.
Okay.
And submitting my resume when there wasn't a position open, but they just needed someone really quick, so that's where those bullet points come from. Yes?
When you created your resume, did you just throw down bullet points and stuff, and then you go to the center of the student union and they helped you with everything, or did you go there with nothing and then they helped you?
I think I went. I can't quite remember anymore. It's been so long, but at least an idea of what you do, and I spent probably hours. I spent an hour there, refined it, went home, and then came back. But at least have an idea of what you do, and they even helped build some of those bullet points. Like, okay, is there anything else? They had me explain what I did, and they helped build some of those bullet points. They definitely taught me how to reword it and make it, like I said, with the maintaining integrity, the cleanliness and integrity of the lab. It's definitely not something I would do. So you can go either way, but I do recommend having some bullet points, at least as a start, to start the conversation.
And I actually have the Career Center guides in my office, and they have sample resumes. They have them online too. They even have a template for science majors on their website now.
Mm-hmm.
But I do have those booklets in my office too, if you want one, just stop by.
Do you like what you do?
I do like what I do. I do think, I like what I do, but I think it's important to just mention that there's jobs that you like to do, but there's also, jobs that it's okay to have a job that allows you to live the life that you like. I think it's good to know that you don't necessarily always have to do exactly what you love all the time. I think there's ups and downs with anything. So I like what I do, but I think it's important to remember too.
And I'll say she's really good at it. She really is. Yeah.
I should mention Leslie Mercer.
Yeah. I think
Now we're in
the training that you guys are getting here it's pretty amazing actually to think. I mean, you say it's been a long time, Megan, but in a long career of working, it isn't necessarily that long, and to see how far you've come and how critical you are to our operations after what I consider to be a pretty short amount of time and an undergraduate degree. And oftentimes, I think that's one of the reasons we wanted Megan to come in, is to recognize that sometimes people feel like you have to go right out and get a master's or figure out some kind of next step. And sometimes the next step can just be being a geologist, you know? And that's really what you are. You're being a geologist, whether you're in the field or you're in the office. And those skills are really important. In fact, they're exactly what is needed in many cases. So
And
That-
I will
that
say
could be
we
an okay
are
answer.
water resources, but I think just in the last year we've hired 2 other undergrads from the geology department. So
Yeah.
just one other group in town looking for good geologists. All right, thank you guys.
thanks.